Hello, everyone. My name is Sebastian, and I'm going to speak about fuzzing. More precisely, I'm going to speak about fuzzing in the context of closed-source applications on Windows. So for the targets that I've chosen, I assume that I have zero knowledge about the program that I'm trying to test. I don't have the source code. I don't have debugging symbols. I only see it from the perspective of a regular user. I'm going to speak about features of which I think that a sophisticated fuzzer should have. And I'm going to mention approaches that exist to implement these features for open source applications. And then going to mention why these features are not going to work if you try to fuzz closed source applications. And then I'm going to mention approaches, some of these I came up with, some already exist and are well known, that we can use to get these features if we want to fuzz closed source applications. Most of the stuff relies heavily on static patching on assembly level, so we might be seeing some assembly in this talk. Let me first say a couple of words about myself. So I'm Sebastian, and I'm working at GoSecure as a pen tester and security researcher. Originally, I'm from Germany, so I'm still a student at Technical University of Darmstadt and used to live and study in Estonia as well. I'm finally meant to graduate from university in December after way too long. I used to play CDF on wingzeroteam.com, which is actually the reason why I ended up in Quebec, because the guy who runs wingzeroteam is a guy from Quebec. I'm mostly interested in low-level stuff, such as binary exploitation, reversing. I got involved into a lot of antivirus and sandbox evasion for my job. And obviously, I also do like a lot of fuzzing as well. But let us first start with the question, what is the intention behind fuzzing closed-source applications? And the main or the most honorable intention would be that we want to find memory corruptions in order to make programs that are widely used more secure. The more corruptions we find, the less likely the program is going to be exploited. I guess that's obvious. At the same time, finding crashes is as easy as it is rewarding, and I find it quite rewarding to find crashes in applications of major vendors such as Foxit Reader or Adobe. And it is not obviously, but actually I was surprised how easy it is to find any crashes in there. A cool thing about fuzzing is that if you implemented your fuzzer well, then your fuzzer runs for you in the background while you have time to do something else with your life. So what my fuzzer does is every time it found an interesting crash, it would send me a push notification, and all I have to do is sit on my sofa and scroll through the crash reports and decide if I want to dig deeper into this or not. Another cool thing about this project is that if you have a working exploit, or if you have a crash that you couldn't exploit, but that looks somehow interesting, you can submit these crashes to organizations such as Zero Day Initiative, and depending on how widely the program that you found the crash in is used, you might even get a bounty for this, so it might even pay off in terms of money. And if I say that finding crashes is actually not so difficult, so the screenshot in the background shows the amount of crashes that my fuzzer has found in 2 months. So this is at the moment 43 unique crashes. This is like 2 months old. I submitted some of these crashes to Zero Day Initiative, which were accepted, and other crashes were submitted to the vendor directly so that they could fix the vulnerability. So what is the idea behind fuzzing closed source applications? And basically it's the same thing as when we fuzz open source applications. All we need to do is we throw random input at our target and hope that our target dies, because we hope that the input triggers behavior that was unintended by the developer, and therefore it doesn't know how to handle it and dies. So while this concept sounds extremely simple, it's both very effective and difficult to master. Because if you want your fuzzer to find deep bugs, so bugs that are hidden somewhere deep in the code base, your fuzzer needs some sophisticated features, because you want to find bugs that nobody else has found before you, right? So these features are actually quite easy to implement if you fuzz open source targets for the reason that we have the source code, but quite difficult to implement if you want to fuzz closed source applications. So, but which challenges am I going to speak about? I'm not going to mention all of these challenges that exist, because you might have some specific challenges depending on the target that you want to test. I'm going to mention 3 challenges that arise when you fuzz closed source applications. And the first challenge might actually sound stupid, but if you think about it, it's quite important. Because how can your fuzzer be sure that no crash has occurred, right? So if you fuzz an application like MD5sum, which is a command line application, what it does is it takes your file, it calculates the hash sum, prints it out, and then exits. So as soon as the program exits, your fuzzer knows that it can start the next iteration of fuzz testing. So we have a metric to know now the program is done doing something that we want to test, and we can start the next iteration. If you test the PDF viewer has a graphical interface. So what it does is it takes your PDF, it parses the PDF, renders the PDF, displays it back to you, and then waits for user input, right? It expects you to click on you or something. So it's not going to close itself because this would be useless. So for this PDF viewers, our fuzzer has a problem because we never really know when it's actually done with parsing the PDF and when is it in the state of just displaying it back to you, and that's not something that we want to fuzz. Another thing is that we want to have good input generation and coverage feedback. So input generation is really important because the behavior of our target depends solely on the input that we give it to, right? Because it's trying to process our input. And coverage feedback is basically a metric to determine if our input was useful or not. Because coverage feedback makes the program that we test export information about its execution with a certain input. So coverage feedback is going to make the program that we test to tell us, I was started with this program, with this input, and with this input, I executed these code areas. And by seeing which code areas have been executed, we can determine if code areas have been executed that we have not seen and tested yet. So we want to have code coverage feedback as well. And obviously, last but not least, we want to have a high number of executions per second, which is obvious because the more number of executions we have, the more tests we can do in a given time frame. I guess that's obvious. So how do we do this for open source applications? And for open source applications, we have very good news because obviously we do have the source code, right? So what we can do is we are able to change the source code to our needs. So we are able to change the source code so that the program behaves in a way that makes it easier for us to fast test it. What we can do is we can make use of a concept that is called Dynamic Binary Instrumentation, and it basically works by adding, hooking, or replacing existing functions either at compile time or in source code itself. And what the instrumentation that we apply to this binary does is it takes care of creating program traces. And the program trace is basically a set which contains information about the code coverage and possibly the memory management, depending on the implementation. The instrumentation is then going to log the traces that were created on disk, so that your fuzzer is able to read them in and correlate a given input to the trace and then see if the input was actually useful or not. Cool thing about this is we have pre-existing tools like Address Sanitizer or ASIN, which is basically a compiler extension. All you need to do is you have to recompile your program with ASIN. It's 2 compiler flags, and ASIN recompiles the program and instruments it at compile time for you. The overhead of ASIN, or for the program that you have instrumented, is quite low. It's only factor 2, so that's not too much. To give you a better idea of how ASIN actually works, so this is an uninstrumented program. As we see, depending on the input, it's either going to call ABC, or only B, or only A, right? That's what the program is doing. And if you compile it with ASIN as such, we see that in each basic block, it has added a call to another function, which is here sanitize. And this extra call takes care of creating these program traces and writes them to disk. And all we had to do for this is recompile a program and add 2 compile flags to it. So that's really, really easy. If we do not have the source code, we actually have a problem. But we can possibly make use of dynamic binary instrumentation. I'm not going to dig too deep into this. It basically works by injecting arbitrary code into an already running process. And the injected code is then running in parallel with the original code and then takes care of creating these program traces for you. We do not need the source code, that's good. And we have already existing frameworks for this. So the most popular that I know is InfillPin and Dynamic. The only issue is that it causes a significant overhead, at least in the way that I have used it so far. We will later see how big the overhead actually is. To give you an idea of how such a trace might look like, here we see a sample trace that was created with Dynamic. So we see each shared object that was loaded by the binary at runtime. So we see each DLL, we see the base address of the DLL, and it gives us a unique identifier. And then we see which basic blocks have ever been executed, while the original order of the basic blocks are retained. So we see that in the first basic block that has ever been executed is in module 13, which is ntdll.dll, and then we see the next basic block that has been executed, and so on and so on. So it gives us a really good feedback about what actually happened in the program, and we will later be using it. So okay, but back to the problems that we had for fuzzing closed source applications. As I said, programs that do not return are a problem for the reason that we don't know when can we kill it, when can we start the next iteration of fuzz testing. For open source applications, again, that's not a big problem, because we have the source code. So all we need to do is read the source code, Obviously, we have to understand the source code. Find the end of the parsing routine, add an exit, recompile the program, and the problem is basically solved, right? Because the PDF viewer is going to quit just at the time when we want it to quit. If we don't have the source code, we can't recompile it, obviously, and we can't apply changes to it on source code level. So what I've seen most researchers doing is they kind of guess when the PDF is done rendering, right? So they start the PDF viewer and then estimate, I think after 3, 4, 5 seconds, whatever, the viewer should be done rendering, and I tell my fuzzer to assume that nothing bad happened, and I kill the program. So they make use of hard-coded timeouts, which is obviously not a good idea because the timeouts are more or less guessed, which basically means that the termination either happens too early, which means there would be more code to be executed, but we never reach it because we kill the program too early, or we kill it too late, which would mean that we waste CPU cycles, right? And as we've seen earlier, we want to have a high number of executions per second. We could also try to measure the CPU cycles that the program takes. So we could possibly start the PDF viewer, measure how many CPU cycles it takes, and when the amount of CPU cycles goes down, we can assume that it's not really doing anything anymore. I tried this, I didn't find it precise, and at the same time, by constantly polling the CPU cycles of a program, you create overhead as well. So and here's what I try to do. So what I try to do is I try to find out if there is a basic block in this program that is always executed, but always executed last for different inputs. Because if there is such a basic block, I can assume that this basic block is executed only if the parsing routine is finished, and that it perhaps waits and blocks for GUI events or more user input. It is important that this basic block is triggered without any user interaction. So to give you an idea of what I'm trying to find, so we have this sample call graph. So for the first trace, the PDF viewer would go like ABEF, then ABDF, and in the end ACF. And what we can see is that the PDF viewer always starts at point F, right? So it never triggers G or H after F. So my goal would here be to find out the location of basic block F and then patch it so that the program actually closes itself. That's the intention behind it. And to do this, what I do is I create program traces of the viewer with a different but valid input. And the traces contain the executed basic blocks in the original order. And then I calculate the intersection of all traces so that I end up with one set of basic blocks that appear in each of these program traces. I choose the last basic block and apply some instrumentation to it. Obviously, while we perform the tracing, we must make sure not to apply any events on the GUI, because otherwise we would end up in a basic block that cannot be reached without user interaction. As an implementation, what I did, I used Dynamic Binary, as you've seen earlier, and I assumed that the PDF viewer would be done parsing after 30 seconds. I think it should be done after 30 seconds. And then I passed the output that we've seen earlier and calculated the intersection with Python, which is not actually worth mentioning here. And then finally, I have a result, which is the last basic block, which is executed in each trace. So now what I want to do is I want to patch this basic block in a way that it force quits the program itself. There's a problem, like how do I patch this basic block on assembly level without corrupting the entire execution binary? Because an exit process on a 32-bit machine might look something like this, right? So you null out a register, push it on the stack, push the address of exit process on the stack, and then return. So this assures that you call exit process with 0. The problem is that this code snippet would be 9 bytes in size. But what would happen if the basic block that we have chosen is not 9 bytes? This would basically mean that we overwrite instructions that are behind the basic block, which would mean that we would corrupt the binary. So we have to make sure that the instrumentation that we apply is as small as possible. And the first approach that I came up with for this is that I add a new executable section to the PE file, which is good because the section has a static address, so I know where it is. And this section contains the exit process routine. And all I have to do is I have to jump to this basic block, which saves me 3 bytes. All I have to do is push the address of section address and then return. So this saved me 3 bytes. I'm now at 6 bytes. That's not enough. We will later see how we can do it better. First, you might be asking yourself, why so complicated? Why do you want to catch an exit process? Right? There must be an easier way. And yeah, there is an easier way. We will later see what it is. Why I do it is because existing fuzzers rely usually, or most fuzzers that I know, rely on the fact that a program returns. And by making the program returning, I can make sure that I am able to use fuzzers that already exist and which might be better than my own crappy implementation, right? So that's the intention behind the exit process. If you want to apply this kind of instrumentation, I would tell you not to do it by hand. This is too frustrating. Rather, make use of Leaf, which is a library developed by Quark's Lab. It literally means library to instrument executable performance. So that's exactly what we want to do. And to give you an idea of how it works, so first we get a handle to the PE file. Then we create a new section, apply certain characteristics to it, such as make it executable. Then we add the byte that encode the instructions for our exit process routine, and then add the section to our binary, and then ask Leaf to rebuild the library, to rebuild the binary. I don't know how Leaf does it in the background, but it works, and that's good. But again, so why it's so complicated? Why do we have to patch an exit process? And as I said, I'm trying to make use of existing fuzzers as possible, but as in my case, I wanted to write my own fuzzer anyway. So what I can do is I override this basic block not with exit process, but with a breakpoint. And the breakpoint is a 1-byte instruction in 32-bit. It's a hex CC. Now all I need to do is write a new fuzzer that is aware of the breakpoint that occurs in our binary, which most fuzzers are not aware of. But if you want to implement your own fuzzer from scratch, that's something that you can do. In the end, if you have chosen to write the exit process, congratulations, you created a completely useless PDF viewer, right? It closes itself, so you will never be able to use it again, but you will be able to fuzz it better. I wanted to give you a live demo of this, but then I decided that a PDF viewer that closes itself is not so interesting. So on the left side, we see the basic block, which is not instrumented, and on the right side, we see a very clean instrumentation. So the last two instructions are basically I push the address of our section and then return so that we jump back to our edit executable section. So that's good because now existing fuzzers do not need to force quit anymore. We can make use of existing fuzzers and we ensure that our PDF viewer is killing itself just at the right time. I automated this process, so I implemented a tool that automates all these steps. And then I ran it on various PDF and image viewers just to test if it actually works. And it worked out for most, surprisingly. So it worked out for Foxit Reader, PDF-XChange Viewer, and other viewers, but not for Adobe. And honestly, I don't really know why it did not work for Adobe. I assume that it is because Adobe is running in its own sandbox. And I guess Dynamic fails to create program traces for programs that are running in its own sandbox. At least that's what I think. So now we basically solved the first problem, right? So we are sure that the program is closing itself just after it has executed the program areas that we are actually interested in fuzzing. To our second problem, as I said, we want to have input generation and code coverage. Input generation because the behavior of our fuzzy, of our target, depends on the input that we give it. And code coverage is our metric to determine if the input is actually valuable or not. So first, how can we get input? What can we do to get samples? And the first thing that I've seen people doing is, let us just read some bytes from def-random and pretend it's a PDF. That's obviously not going to work. We could also try to specify certain grammar rules for our input generator. So we generate input from scratch and specify certain rules and how the input should look like. So what we do is we specify a rule like if you want to create an HTML document, it has always to start with the opening HTML tag and it has always to end with the closing HTML tag. We could possibly make use of genetic fuzzing, which basically means that we try to learn the file format on the fly. So we give the input, we give our target some random bytes, see if it triggered any code areas that we have not seen yet, and then try to correlate the bytes that we gave it to the basic block that have been executed, and then slowly try to understand the file format from scratch. What we can also do is we can make use of mutation-based input generation, which basically means that we take input of which we know that it's valid, and then corrupt it. So basically, we take a PDF of which we know that it's valid, corrupt it, and give it to our PDF viewer. So let us first take a look at our random input approach. And that's usually completely useless, because the idea of a file format is that to specify that our bytes must have a certain pattern. So for example, a PDF, the file format of a PDF says that it always has to start with PDF, these 3 bytes. If these 3 bytes do not occur, then the PDF viewer is going to tell you, that's not even a PDF, I'm not even trying to render it for you. So in our process, we would never be able to hit the process function, and even less likely, we would be able to find a bug in the process function, right? What I prefer doing is, I prefer making use of a concept that we call mutation-based input. So as I said, I take a PDF of which I know it's valid, apply certain corruptions to it, and then feed it to the PDF viewer. The problem is, which PDF do we choose, or which PDFs do we choose? Because a PDF is a really, really mighty file format, right? It can do a lot of things. It can do stuff like it has checkboxes, it can verify digital signatures, it has 3D objects in it, and so on and so on. And we want to have input that covers basically all of this. And you will never be able to find a PDF that covers all of these functions. So, and at the same time, you don't want to scroll through all the PDFs that you might find on the internet just to find out if there's a PDF that triggers something new. At the same time, we want to avoid redundancy, which basically means we have two PDFs in our test set which trigger the exact same behavior in our PDF, because this would be redundant. The same behavior is triggered twice, we would be ending up testing the same behavior twice. So in order to overcome this issue, there is an approach for this which is called Corpus Distillation. And Corpus Distillation basically works by first collecting a huge number of valid corpuses. In my case, I took 80,000 PDF files simply by crawling the internet, and that's not even a lot. So I've seen researchers collecting around millions of PDFs or millions of different input samples, and then doing corpus distillation on it. So first, how can we get those inputs? We could possibly make use of search engines, so we crawl the internet, or we use test sets of open source PDF viewers, such as PDF-Hum. They export the PDFs that they tested their product with. And then we measure the code coverage for each corpus, so for each PDF that is in our test set. And so I start the PDF viewer once with each PDF, and then get the code coverage, and check if a new behavior was triggered, if any new basic blocks have been executed. If this is not the case, so if this PDF triggered a behavior that I've seen already by a previous PDF, I can kick out this PDF because this would be a redundant PDF in our corpus. So in the end, if you do this, you end up with a set of PDFs of which each triggers a unique behavior in your PDF viewer. And at the same time, it avoids redundancy in your PDF. So as I said, we need code coverage to do this corpus distillation approach. Obviously, for open source, no problem, just recompile the program with ASIN. But what happens if we don't have the source code? We could possibly try to apply the same instrumentation on assembly level as ASIN does. But as we've seen earlier, it's really easy to corrupt our binary by doing some assembly magic. So we could possibly make use of dynamic binary instrumentation, right? This helped us for our first problem, why wouldn't it help us for our second problem? And as I said earlier, the problem is speed, or at least performance. So to show you how big the overhead actually is, I patched Foxit Reader, which is a random PDF viewer, with the auto-exit approach that I mentioned earlier, and then measured the time until exit process was finally called. And the uninstrumented version of Foxit Reader took around 1.5 seconds to call exit process, while with Dynamic Rio, it took 6.4 seconds. So that's an overhead of almost 5 seconds, and that's obviously nothing that we can use for fuzzing, because we want to have a high number of executions per second. So if you want to do corpus distillation with Dynamic Rio, it will take you 6 days for 80K PDFs. That's way too long, and at the same time, as I said, 80K PDFs is not even enough. You want to have millions of PDFs in your set. Okay, so let's try to get a bit creative. So what can we possibly do? We could possibly try, as I said, to apply this instrumentation on assembly level, but we've seen it's very easy to corrupt the binary by changing the instructions on assembly level. At the same time, we would have to fix all the relative jumps and relocate instructions and whatnot. I don't want to do this. So we basically need an instrumentation approach for basic block coverage. The less bytes we have to change, the better, because the less likely we are to corrupt our binary. And obviously, it must be very performant and scaling at the same time. And a well-known approach that exists for this is that we make use of breakpoints again. So as I said, a breakpoint is a 1-byte instruction, it's hex CC. And then what I do is I overwrite the first byte of each basic block that exists in the binary with a breakpoint, statically on binary on disk. And then all you have to do is implement a custom debugger, which at one time, it starts the program and fetches all the breakpoint events, overrides the breakpoint with the original byte that it overwrote it with, both in the address space and on disk. And then we decrement the instruction pointer and resume the execution. So now you might be thinking, but this is crazy, right? Each basic block is going to trigger a breakpoint which we would have to fix, so the overhead must be even worse. Actually, it's true, but it's only true for the first iterations, because as we undo the instrumentation for the basic blocks that we have already seen, we ensure that only those basic blocks that we have not triggered yet are going to trigger a new breakpoint, because we undo the instrumentation for the basic blocks that we have already found during our execution. So I assume that after the first iteration of testing, we almost run in real time again, because most basic blocks instrumentation has been undone again. Let us see how this works. So to get an idea of this, again, I patched Foxit Reader with the auto-exit approach. Finally, it kills itself, right? And then I implemented a custom debugger in C++. I say it like it's super easy, but it took me like a month. And then I patched all basic blocks that appear in Foxit Reader. And this was a number of 1,700,000 something basic blocks. I have not done this by hand. Obviously, I wrote a script for this. And then I ran my custom debugger on this. And on the first iteration, as we have assumed, the overhead was like crazy, right? Because 48,000 something breakpoints had to be fixed at runtime. At runtime, the original bytes had to be looked up, overwrote on disk, and in address space, and so on and so on. So this took 16 seconds. That's way more than for dynamic binary instrumentation. But for the second iteration, most basic blocks have already triggered. So this means that only new basic blocks will trigger. So in the second iteration, only 2,000 new basic blocks have been hit by the next PDF. And this was only 2,000 more, and so it was only 2 seconds until auto-exit was called. And for the third iteration, I took a PDF that would trigger the exact same behavior as a PDF that I've tested with earlier. Obviously, I didn't have any overhead anymore, because there was no breakpoint anymore that was triggered newly, right? So I was running with 1.5 seconds, and if you remember, this is running in real time again. So on the right side, left side, we see the basic blocks, and the first instruction, as I said, is added in 3 event, which is basically a breakpoint in x86. As I said, this is a well-known approach. I didn't come up with it myself. I got it from a guy that is called Janos Kapp from Estonia. He open sourced this Python implementation. I wrote it in C++, and he described it a bit better on his talk. So to recap, now we basically have solved 2 big problems, right? We made sure that the PDF viewer is finally killing itself just at the right time. And at the same time, we are able to measure code coverage with very low or almost 0 overhead in case it does not trigger any new basic blocks, right? So, but we had a third problem, which is speed. We want to have a high number of executions per second. What could we possibly do here? And I asked myself, so what is the biggest bottleneck for fuzzing, right? And the biggest bottleneck is that you have to restart your program for each iteration. Each time you give it a new input, you have to restart the program that you test. Restarting a program basically means that the operating system has to create space for the program, has to allocate space for the program. It has to load all the libraries and do a lot of other stuff as well. So this creates a lot of overhead. But at the same time, we are absolutely not interested in fuzzing the start of the program, because starting a program, or while starting the program is not going to handle our input. So we want to try to avoid that we have to restart the program. That's the approach here. For open source applications, again, it's not so difficult. All we have to do is we can make use of a concept that we call fork servers, which basically works by you start the process and suspend its execution on the first line of main or wherever you want it to. And you suspend its execution at a point where you know that it loaded all its libraries. And then you kick in the instrumentation, which forks the process. And Linux fork basically means it creates a complete copy of the program, which includes all the libraries and so on. And so we have an exact copy of our program that we want to fuzz, and then resume the execution of our copy. So by doing this, we avoid that we have to restart the program, because all we do is we take a snapshot of an already running process and resume its execution. This is cool because we avoid, so the parent process never exits, and the snapshot has all its loaded libraries and a complete snapshot of its memory layout. Obviously, Windows does not know the concept of fork, and we don't have the source code. So what are we going to do this time? Again, so we need to find a way to speed up executions without the source code and fork. We want to avoid to restart the program. We usually have 2 observations. So even though we don't have the source code, we are usually able to figure out where the location of the main function is. And as presented earlier, we can find out what the last basic block is that the program is executing. So We see here a small code snippet, and we want to try to fuzz test this code snippet without having to restart the program. All it does is it takes one argument, passes it to process, and what process does is it prints it out and then performs a very obvious stack-based buffer overflow. And our goal here is that we want to fuzz the process function. We have two observations, even though we assume that we don't have the source code, but finding the main function would be quite easy. And at the same time, our user input, our argv, is on the stack. And what I like to do is I like to patch the first line of main and the last line of main. So the first basic block and the last basic block, each with a breakpoint. So I frame the code areas that I'm actually interested in fuzzing. And if the main breakpoint triggers, all I do is I store the context, the execution context. So I store the CPU registers, I store the flags, and so on. And then I try to find my user input in memory, so in this case, argv. And then I undo the first breakpoint because we don't need it anymore. And then what I do is, if the second breakpoint triggers, we restore the execution context, we restore the CPU registers, we restore the flags, we restore the stack, and so on. And then we mutate argv, because we found our input on the stack, so we mutate it in memory, and then put the instruction pointer back to main, right? So that it runs in a loop. We avoid that the program has to close itself. I tested this approach for the sample program that we've just seen, and the results are surprisingly good. I tested it with 1,000 iterations, and with the usual approach of having to restart the program, it took like 10 seconds. With the in-memory fuzzing approach, it took me half a second for 1,000 iterations. I think we can all agree that this is a massive speedup. It's not always that easy. So, as you've seen, the code snippet that I've just shown you is very trivial. It does not do a lot. For a program such as a PDF viewer, we have a way bigger execution context to restore, right? The PDF viewer has separate threads. PDF viewer takes care of, like, it has a graphical interface, it holds handles, and so on and so on. At the same time, it does a lot of stuff on the heap. So we need to take care of that we free memory that has been allocated. That's not very difficult to do for the stack, because all we have to do is reset the stack pointer. But for the heap, it's a problem, because what we have to do is we would have to hook the malloc or allocation function so that we have pointers that we can individually free again. This is a lot of overhead again. The same goes for the handles. What we can do is, for smaller programs, as we've just seen, what I do is I just don't run the fuzz loop forever, because it would run out of memory at some point. But yeah, that's not something that we can use for PDF viewers, but for smaller command line applications, that's something that we can do. So finally, what have we seen? So we made use of dynamic binary instrumentation to identify code areas in our PDF viewer that we are actually interested in, so that we finally made our PDF viewer killing itself when we're not interested in it anymore. We made use of small instructions to signal our fuzzer, in this case breakpoints, as a way to communicate between fuzzer and our target. We made use of a custom debugger to handle our instrumentation, and we've seen that we can generate block coverage with low or near null overhead, in case, remember, if no new breakpoints are triggered, only by using breakpoints and using the concept of uninstrumenting or undoing the instrumentation for code paths that we have already seen. And we have seen that in-memory fuzzing is both extremely fast, but as I was trying to tell you, it's really difficult to implement for a big project. Right? So that's what I wanted to tell you. Thank you for your attention.